All right, here's the first homework of our second unit, math of change. We're going to start by looking at the average rate of change of a function over an interval. We talked about in the notes change. You can find change by subtracting two numbers. And the change between 15 and 3 is 12. But it means very little unless there's context. So if you have a function and you have the point 3 and then you have the point 15, it's different if they are separated by one x coordinate, because then we are changing 12 units over one x coordinate. It's different if there was 19 x coordinates between those 2 points, because then I'd be changing 12 over 19. There would be a little bit less than 1 y increase per x. So we need this change in context. And in the context provided the x coordinates, maybe that we're looking at between, 15 was at an x coordinate of 2, 3 was at an x coordinate of 1. So these would be, 12 y's that we've gone up for every x that we've gone to the right. So keeping that in mind, let's look at x cubed from 2 to 3. It's very easy. All you need to do is find the points. 8 is our y coordinate. 27 is a y coordinate. We have gone from 8 to 27, the difference being 19, over the course of one x value. 3 to 2, 2 to 3. Just make sure you keep things aligned. We had a change of our x's of 1. 3 went to 27, 2 went to 8. So 19 y's we've gone up for every x that we've gone over, on average. Between 2 and 3. And I'll write that just for this one. On average, f of x went up 19 y's per x from x equals 2 to x equals 3. Okay, let's just do others, and I'll just vocally do the statement. Find f of 3, 9 times 2, 18, minus 9 plus 2, 11. F of 0, 0 minus 0 plus 2 is 2. Okay, so we've increased 9 y's over 3 x's. On average, we've gone up 3 y's per x from x equals 0 to x equals 3. We don't always go up. Functions go up and down. Sometimes functions are stagnant, all depending on the situation. Let's look at this guy. Pi over 3, we have a trig function. Let's think cosine 2 pi over 3, 2 pi over 3 right here, cosine. That horizontal distance is going to be negative 1/2. Cosine of 0, 1. We will find the change in my y's divided by the change in my x's. I'm being careful here. I'm doing 1 minus negative 1/2. That means the 0's got to go first. That'll find the change in my x's. So actually, this is good. If I do the math, I see I have some negative change. I have the point 0, 1, and then the point pi over 3, negative 1/2. So my function on average has gone down. Now we can make this look a little nicer. Got 3 over 2 times 3 over pi. That's negative. So this will be negative 9 over 2 pi. So on average, the function's gone down 9 y units for every 2 pi x units, or it's gone down 9 over 2 pi y units for every 1 x unit. So negative growth, we're going down from left to right. Let me make this look a little nicer. And you know, I probably should have stuck with the second y first, you know, the y for pi over 3. That way it's easy to see. For the key, I'll make this adjustment, but it doesn't matter. You could do the change in the x's first from like right to left, and then the change in the y's will just be opposite what the change in the x's, the change in the y's would be from left to right. So as long as we're consistent, we're going to get the right answer. So I can say f of x on average is gone down 9 over 2 pi y's per 1x, or f of x on average has gone down 9 y's per 2 pi x's. Either way. All right, 2 to the negative x. Let's see. We got f of 4 is 2 to the negative 4th. That simplifies to be 1 over 2 to the 4th, which is 2, 4, 8, 16, 1/16. And then f of 1, 2 to the negative 1st, is 1 over 2 to the 1st, which is 1/2. So let's see. Y2, or my second y coordinate minus my first y coordinate, this ends up being 8/16. This will be a change of minus 7/16. But the context is 4 to 1, 3. So we have minus 7/16 times a third. That can simplify to be minus 7 over 8, 48. Okay, and this would be my average rate of change. So on average, 2 to the negative x between 1 and 4 decreases 7 over 48 y units per every 1 x unit. Oh, this is a good one. Start with our first y coordinate. 4 minus 15, negative 11. And then I already know what the answer to this is. So like, why do I know the answer to this? This is like a straight line. The slope is negative 3. We are going to be following that slope consistently. Every single x unit, I know we're going to be changing by, you know, negative 3 y's per x. And I know over an interval, we're changing by negative 3 y's per x, or decreasing y's per x. I'll show you how this is guaranteed to be negative 3. Y2, changing my y's, changing my x's, negative 12 over 4, booyah, negative 3. On average, my function f of x has gone down 3 y's per every 1x from 1 to 5. We will find that at every single location we'll go down 3. Oh yeah, tangent. So we've done a bunch of decreasing functions on average. Let's see if tangent is an increasing or a decreasing function on average. I know the tangent of 3 pi over 4 is -1. Sine over cosine, root 2 over 2, and negative root 2 over 2. Pi over 4 is +1. So this function looks like it's decreasing as well. Because I go from the point pi over 4, 1 to 3 pi over 4, -1. On average, the function decreases. Figure out how many units on average it decreases. I like to start with the second y for the later x to help my context. So -1 minus 1 over 3 pi over 4 minus pi over 4. Gone down 2 y units for every 2 pi over 4s, which simplifies to be pi over 2 x units. This simplifies to be -2 times 2 over pi, or -4 over pi. I'm going to just write this statement out. On average, the tangent function decreases 4 y's per pi x's, or decreases 4 over pi y's per 1x. All right. What is the visual representation of average rate of change if you are looking at a function? So for all of these graphs, like take this graph, if I want to find an average rate of change between 2 points, what I am doing, finding the change in y's over change in x's, is I am finding the slope of this line. Now, the slope of this line, being the average rate of change, is what we call the slope of the secant. Secant being a term we've used before in geometry, saying a line that crosses a circle at 2 points. But here in this math class, we're just going to say it's the slope of the line that is connecting 2 distinct points on the function. Okay, so slopes of graphs tell us how quickly graphs are changing over intervals. Okay, that's very important. Slopes are important. Slopes tells us how quickly things are changing. We are going to find the average rate of change of the function over the interval. We got 2 to 4. I'm going to just go ahead and use different points here from 2 to 4. The slope of this line okay. So I can see that the slope is negative, so my average rate of change is negative. So my function is decreasing on average between 2 and 4. I have the y-coordinate of, we're going to call this -2. I know it looks like it's at -1.5, but I really meant to have it be right on this whole number. So I'm going to use this -2. If you watch the video, you got hooked up there. The y-coordinate up here is +2, so I can see I've gone down 4 y-coordinates, but let's give it context. Over 2 x-coordinates, my average rate of change is -2 y's per x over this interval. Let's do -1 to 4. I'll use red stars. From -1 to 4. Okay, so I have this line. I'm going to pretend like this is a horizontal line. It's not a horizontal line, but let's pretend. So I got the point -2 for my x-coordinate of 4. I have the point -2 for my x-coordinate of -1. I've traveled 5 x units. This ends up being 0 over 5. On average, my function has increased 0 over the interval from -1 to 4. Now, we can see it doesn't just stay flat and doesn't increase or decrease, but it does increase the same amount that it decreases, so that on average, it ends up back where it started. All right, fantastic. To change gears, we are going to talk about what is going on at an exact location. What is happening right here at 3, or what is happening right here at 1? How quickly is the function going up or down? All right, so let's first read here. To approximate the exact or instantaneous rate of change of a function at x equals 1, we can examine the average rate of change using points surrounding that location. So it says, hey, you want to know what's going on right here at 1? Why don't we use 0 and 2? Why don't we look at the slope of the secant there? Why don't we use, you know, a half and 1.5? That'll do a better job, okay? But we're going to even go further away, and we're going to say from -1 to 2, or -1 to 3, and then from 0 to 2, and from -2 to 4. So just starting with points very, very far away, we're going to start getting closer and closer and closer, and we will be able to see that the closer we get, the better our approximation for what's going on exactly at 1 is. So between -2 and 4, I'll have a y-coordinate of -2, a y-coordinate of 0 for -2, x-coordinates 6, x-coordinates. I can see I have some decreasing slope between here and here. Okay, now that's not correct. We can see that my function is increasing right at 1. So if it's increasing right at 1, we know that this negative value is not correct. Okay, let's go -1 and 3. All right, well, -1, I got -2. 3, I got 0. So 0 minus -2. I can see I'm going up in my y's over my x-coordinates that I've gone over 4. From 0 to 2. Okay, now we're talking. From 0 to 2, I'm going to get this line. This slope, I can see, is starting to get better. It's looking better. This looks like it's a little bit steeper, but it's a better and better approximation the closer and closer I get to 1. So 2, I got 2. 0, I got -1.5. So this is an increase of 3.5 over 2. 3.5 is 7/2. So I'm increasing 7 y's per 4 x's, or 7/4 of a y per x. Okay? Each one is giving me a better and better approximation. What is the visual representation of the instantaneous rate of change if you are looking at a function? We will say it is the slope, not a secant line, but the slope of a tangent line. Now, a tangent line is a line that's just touching your function at one point. You're familiar with that from geometry. But it is created, line touching the function at one point. But we will talk about how it's created in a second. Touching the function at one point. Well, let's talk about how that's created, okay? How it's created is we will take these 2 points from 0 and 2. Got our slope. slope is a decent approximation of what's going on at 1. And we'll start using points that are getting closer and closer and closer together. And these slopes become better and better approximations for what's going on at 1, till we have 2 points infinitely close together. Now, the closer and closer you put the points, obviously the little line segments are going to get smaller and smaller, but for any line you can connect and extend. And when you connect and extend, you create that tangent line. So it's created by taking 2 points infinitely close to each other, connecting and extending those. Let me just kind of put this here. Like that. And let's go back to 2 and 2. I say it's a decent approximation for slope at x equals 1. But we can do better. And we're going to do that with this function x cubed. Okay? We're going to try to find the instantaneous rate of change at 3. So let's first start by looking at y equals x cubed. I'm not going to be able to see the point at 3, so I'm going to go ahead and change my window a little bit. That way I can kind of see what's going on at 3. Okay, so I can see at 3, it's definitely apparent that my function is going up. Okay, but how quickly is it going up? Well, what I could start with is, let's change it to that. Okay, well, what I could start by doing is looking at the points between 2 and 4 and finding the slope between those 2 points. That'll be a decent approximation for what's going on right here at 3. Okay, and that's the slope equals what? So let's use our trace. That way we can find quick function values. 4 is 64. 2, 8. 4 minus 2. 64 minus 8. 56 over 4 minus 2. 28. I feel like my function is really going up quickly. It's going up 28 y's per x at 3. Okay, so here's my first approximation. Let's do a better job. Let's now look at 2.5 and 3.5. Okay, so that will put my 2 points closer together. Now I'm looking right here and right here. Okay, I'm going to get a better approximation. So I got 42.875, 2.5, 15.625. So I'm looking right here and then right here, 15.625. Over a change of 1. Okay, let me just really quickly find 3. So 3 is right there, so I'm looking for the slope right there. All right, well, let's see what this approximation will be. And I know it's going to be better because it's closer to what's going on right here at 3. So 42.875 minus 15.625 over 1. 27.25, okay. So my first approximation was 28. I can see a better approximation is 27.25. So, better approximation for my slope at 1 is 27.25 y's per x. Let's do a better job. Let's use 2.9 and 3.1. So now I'm going to use points that are even closer. So let's see. We got my point at 3 right there. Let's use the point just to the left and just to the right. Let's use 3.1. I get a y coordinate of 29.791. And 2.9. 24.389. These are nice, easy decimals to work with. Divided by 3.1 minus 2.9, that's going to be 0.2. Okay, so using these 2 points to approximate the slope right there, let's see what I get. 29.791 minus 24.389 divided by 0.2, 27.01. I can start to see, man, my approximations that I know are getting better and better to saying what is exactly going on at 3. My slopes are getting closer and closer and closer to 27. I don't know why I said slope at 1, slope at 3. All right, let's see if it's really true. If I go just to the left and just to the right of 3, like I'm talking about getting really, really close, closer and closer to just going at 3. If I find the slope between these 2 points, it's going to be a better approximation. So 3.01, that y coordinate is 27.270901. Okay, 27.270901, 2.99. 26.730899. Okay. Divided by 3.01. 2.99. That's going to be 0.02. I'll just double check that. Okay, let's do the calculations. $27.270901 minus 26.730899 divided by 3.01 minus 2.99. Oh gosh, isn't that great? It's getting closer and closer and closer to this exact value. This exact value looks to be 27. I'm going to say this is even better approximation for slope of f of x at x equals 3. That would be the instantaneous rate of change at x equals 3. Now, could we continue this process? Sure. We'd probably get 27. Could we do this without a calculator? Heck no. Try doing this calculation by hand. Not possible. Try doing this calculation by hand. Not possible. So, what mathematicians did back in the day is they needed to approach this differently, okay? They needed to figure out a different way of finding these values, 27, without using these simple calculations, okay? I'm going to save this right now. That way I don't mess up what it looks like, and I think I already did. Sometimes when I zoom out, it like messes up. All right, that looks nice. That looks nice. All right, everything looks nice. All right, now we're going to zoom in. So what they discovered was the existence of this f prime function. This f prime function is going to show us the slopes of the tangents to f. Okay, so what we're going to do is just pick some points, you know, like here, 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 and here. Then we're going to look at the slopes, okay? Now, if I drew like a slope right at this point, I could see we have a very positive slope. It's going up from left to right. Right here, I have a less positive. I'll just draw a smaller positive. Right here, this slope looks to be very close to 0. This slope, a little bit positive. This slope right here, very positive. Well, I'm going to plot those values. So I'm going to plot the slope values, where it's like bigger positives, less positives, 0, less negatives, bigger negatives. I'll probably put those over here. Well, I had like 5 points that I looked at, these x values, and I had at -2 a bigger value. At -1 I had a smaller positive value. At 0 I had 0. At 1 I had a smaller positive value. At 2 I had a larger positive value, creating this type of graph. If I could look at even more points, I would see, you know, slopes are going to be in between. Okay, in between. Slopes to the in between 0 and 1 would be a little bit less than. So a little bit less than. So it actually works out that I could connect and extend these points because the slopes do follow this track. Well, this is like a graph of some function that's familiar to us. So there is some equation for all the tangent slopes to f. And it actually looks like some x squared equation. Okay, let's look at this one. What if I started with some quadratic? Well, let's again do kind of this process with maybe 4 points. I can see very positive, less positive, again 0. Now we're talking about a negative, and then a even greater negative. So if I'm plotting the tangent slope values, and it's very positive, less positive, 0, negative, more negative, I'm going to have my 5 points. Very positive, less positive, 0, negative, more negative. And I can see it's starting to follow this line. So there's some sort of equation for this quadratic that is like a straight line. And this straight line, if I look at any point like here, I see, okay, I should have a positive slope. It's less positive than -1. Well, here I have a positive slope. Okay, so this function is telling me the tangent slope values at any location to this original, this f prime function. Look at this. like an exponential function. Okay, so I have a very, very small, close to zero. It looks like it's very teeny tiny positive. This is a bigger positive. Here, this is a larger positive. Here, an even larger positive. So if I'm talking about positives getting more positive at these locations, I kind of only did 4 locations here. Tiny positive, more positive, more positive, more positive. Maybe I have a graph that looks like this. It's very similar to the original graph. It's just kind of shifted to all positives. Let's look at this guy. I only have a couple points just to the right of the x-axis. I don't have a point at 0, but I'll just look here. I have a very, very, very large positive. This slope, less positive, it's like 1. This slope, less positive, it's like maybe a half. This slope, less positive, maybe it's like a fourth. So if I were to look at these guys, I'm probably up here, then like here, then like here, then here. So very interesting, this graph. But the key is that like there is some function. Like these are graphs that have equations to them. And if we have the equation of this graph, we could plug in an x value into the equation and we'll find a slope value. That's what mathematicians had to do because they didn't have calculators. They had to find the equation for this. And then it made life really, really easy. Let's finish off with this one. This is a good one. So we got that. I'm going to go here. I'm going to go here. I'm going to go here. I'll go here, here, here. So starting off, very negative. Here, I got 0. See, horizontal tangent, 0 is the slope. Then I'm going up, it's positive. Flattening out, this is close to a 0. Back to going down, I got a negative. Back to flattening out, I got a 0. Back to going positive. So it looks like I got positives, zeros, and negatives. Let's see what that looks like. I got 1, 2, 3, 4, 5, 6, 7 points. So 1, 2, 3, 4, 5, 6, 7 points. Starting with large negative. Then at -2, 0. Then at 0. At -1, positive. Then at 0, 0. At 1, negative slope. At 2, 0. At 3, positive slope. Oh man, this is really cool. This is looking like some sort of cubic. Not pretty, but you get my drift. And there is an expression, there is some sort of equation for this that produces this graph. And if you plugged in any x value, got the y value, it's going to tell you the exact slope of this original function. So like at -1/2, I see I have a positive slope. At -1/2, I see I have a positive tangent slope. You can see it's less positive than what's going on at -1. Okay, it's less positive. You can see it's not 0 at 0. Okay, so this is the idea. And we discovered these formula. These formula are formula for the slope of tangents. These formula were created by taking 2 points and putting them infinitely close together. So it's like slope formula, y2 minus 1 over x2 minus x1, which is we are just using. But we're going to take 2 points, put them infinitely close together. Let's do dir. Okay? Like here, f of x minus f of c over x minus c. If I plugged in c, I would get 0 over 0. Okay? But the idea is that I'm approaching c. Now, we remember if we have 0 over 0, the limit exists, but you're not allowed to plug in the exact point c. Well, in this situation, we said, take this point c, f of c, on this function. Maybe it's like this, something like that. And if I take another point at x, f of x, but I take that point and move it closer and closer and closer and closer to c, we'd be able to find the slope of that point. Okay, so it's infinitely close, and this would be the slope of the tangent to the function at c. Here, it's for any x value. This is just x and f of x. It's like for any x value, you can change this to any value, like 3, and this would give you the slope of the tangent at x equals 3. Okay, and we walk through developing these formulas in our notes. We need to be able to translate this. So given the graph of f of x, this is f of x, sketch the visual representation of the value, stating the value is positive, negative, or 0. So this looks very similar to our first equation, f of x plus h minus f of x over h. We understand this is the slope of the tangent at x. Well, instead of x, there's d. So I need to translate this to the slope of the tangent of f at d. Well, here's d. Here's the point at d. I can see that the slope of the tangent to d is going to be negative. Less than 0 is negative. You could say, just for now, that it is negative. That is the same as this. This is very similar to the limit as x approaches c. I mean, it is the same form as the limit as x approaches c of f of x minus f of c over x minus c, which is the slope of the tangent to the function at c. But instead of it being c, it's d. So, boom, d, d, d. This is the same as this. Okay? Two different forms meaning the same thing. Now notice these two has no limit. It's just talking about the point at D and the point at C. Here's the point at D. Let me use a different color. Here's the point at D, and here's the point at C. And it's asking about the slope between those 2 points. Well, that slope is negative. This is the slope of the secant. This would be the slope of the secant between, yeah, sure. I'll do blue and then highlighted. That's the slope of the secant connecting D and C. This is the slope of the secant connecting C and A. So, connecting C and A, I can see that this slope, that's a positive slope. This would be the slope of the tangent at C. At C, the slope of the tangent looks like we have flattened out. That is a value of 0. This is the slope of the tangent at B. This is the alternate form. So using my alternate form, I read this as f prime of b. At b, my slope of my tangent is positive. Greater than 0 is positive, less than 0 is negative. Okay? So there we go. Okay, now we walked through this in class, how we can use this formula to create this equation. So it turns out, if I have the graph of y equals x cubed, that using the formula, we can create this function whose expression is f prime of x equals 3x squared. This is an expression where if you plug in x's, you'll get slopes of tangents to f, okay? We found that. We could find that. And I said here, using this formula, it can be found that f prime is 3x squared for f of x equals x cubed. What does f prime mean? F prime of 3 means the slope of the tangent to f of x at x cubed at x equals 3. What is f prime of 3? Plugging in 3 into 3x squared, I get 27 even. We should not be surprised by this because we did later finding that the slope, a good approximation for the slope at 3, using 2.99 and 3.01, was 27.001. All of our approximations got closer and closer and closer to 27. That is going to approach 27 as our points got infinitely close together. So that we would say that the exact value, as you continue to get better and better and better, you get closer and closer to 27. So the best approximation, it would be approaching 27. So this is not surprising we saw that. But look, we find it using this expression. If I ask you what is f prime of 1? Slope of tangent to x cubed at 1. 3. The slope of y equals x cubed at x equals 1 is 3. Now what does this mean? This is what we call a derivative. This is a derivative function. This is a tangent slope generator for the specific function x cubed. This derivative function, tangent slope generator, is the instantaneous rate of change. It tells you how quickly the function is going up or down at a specific moment. We would say at x equals 3, f of x is going up 27 y's per x. This is super important. This is calculus, instantaneous rate of change. This is what calculus is all about. Instantaneous rate of changes. Okay, well, what is f of 3? Well, I know I have the point 3, and then 3 cubed is also 27. So this is the point. So at the point 327, it just so happens, and this is just a coincidence, that the slope is also 27. And the equation of the tangent line, y minus y1, this is from here, is equal to my slope, which comes from here, times x minus x1. Remember, equations of lines can be left in this form. We do not have to simplify it. It will be nice to simplify it when I graph 27x minus 3 plus 27 is a quick and easy way to solve for y. And you should see, that's beautiful. There's my tangent line that I kind of sketched. The slope is 27 at this point that is just touching my function once. Let's do it with 2. F prime of 2. Slope of the tangent to f at 2. 3 times 2 squared. 4 times 3, 12. F of 2. 2 cubed. 8. At the point 2, 8. The slope of the tangent equals 12. Creating this equation. Boom. Watch. 12. X minus plus 8. I'll see a beautiful tangent line passing through this point 2, 8. The slope of this line is 12, and it's telling me how quickly the function is changing at that specific moment. Let's do negative 2. Also 12, but the point is at negative 8. So at the point negative 2, negative 8, slope is 12. Y plus 8 equals 12. X plus 2, let's see. At the point 2, negative 8, I can just barely see it on my graph, that's fine. I have the equation 12 in purple, my daughter's favorite color. X plus 2, and this time when I solve for y, I'm going to be subtracting 8. Gosh, it's great. Right there. So at this point, negative 2, negative 8, there's the equation of my tangent line. It is telling me that at x equals negative 2, my function is going up 12 y's per x. It's the instantaneous rate of change of my function. All right, that was a lot. It was a long video. I hope we understand what we're doing here with change in math. Slope of secants changing into slope of tangents, telling us exactly how quickly something's changing at a moment in time. Let me know if you have any questions. Come in with anything at all.